Okay, everyone, so welcome back. We're talking about probability, and the last concepts that we saw were regarding conditional probabilities. And just as a recap, we know that a conditional probability is a probability or a likelihood of something, probability of something happening given that some other event happened first. So it's the probability of E given H. And we know that if H already happened, and you're interested in E, actually your probability, you're interested in this probability here of both happening. But we know that we have to correct for the sample space changing. We have to kind of do a normalization of whatever comes first. Okay, so in this case, H comes first, and this is the formula for conditional probability. We're going to talk now about a particular case of events called independent events. So what are independent events? Well, events E and F, and they in the same sample space, are called independent if the conditional probability is equal to what we call the prior probability. So what this means here, let's break this down. It means that the probability of E given that F happened first is equal to the probability of E. Meaning that F happening first didn't change my original probability. So I had an original, what we call a prior probability of having event E happening. And if this probability, if we evaluate the probability of this event E happening after F, well, it's the same. So this means that F has no impact in changing the likelihood of E happening. And the same will hold for the contrary sequence. So this here says that the probability of F given E, meaning that the probability of F event, the event F, happen after E has happened, is equal to the original probability of F, meaning that E doesn't affect the probability of F, right? So when the first event don't change the likelihood, don't change the probability or the likelihood of the second event. When this happens, when you have this, we are talking about independent. They are said to be independent events. Okay, so let's analyze a special consequence of this. So if we're saying that the probability of the original probability is equal to the conditional probability, meaning that nothing changed, and we know the formula for the conditional probability, so I'm going to expand the formula of the conditional probability here in the right hand side. What we know is that the original probability then will be equal to the condition, and in the end of the day you have this property where the probability of both things happening is just the multiplication of the probability of individual events. So this holds only for individual events. Okay, it's a consequence of assuming that the first event won't change the likelihood of the second event. Okay, so this is what I'm kind of expanding this term here, and we know that E must happen with F because F happened first, and I'm interested in E happening. So both has to happen, but I have to normalize, and I normalize but whatever comes first. So in the end of the day, the original probability is equal to the formula of the conditional. Okay, and if you multiply, if you pass this term here multiplying to the left, you will see that this formula here, this condition hold for independent events. Okay, but independent events is really about, interpreting and having a feeling of what's happening. Obviously that you can check for independency, for the independent condition, but I'll give you some examples so that you can see how interpreting and feeling if one event changes the other is actually the right way to go. Okay, so here's the problem. So let's take an event K as drawing a king from a deck of cards. And C as I'm drawing a clubs from a deck of cards, okay? Deck of cards. So I want to know if these events are independent or not. Okay, so let's reason. So the probability of drawing a king, it was originally what we call a prior, so we didn't have any event happening first. Now let's think about what would happen with the probability of drawing a king, given that I've drawn a clubs first. Okay, so to check for independence, we have to have these probabilities to be equal. Or you can think about reasoning and knowing if the probability would change. So let's think about this. If you draw clubs, what does this inform you about drawing a king? Well, actually it doesn't change anything, because if you draw clubs, you could have drawn any a card. So it doesn't make the chances of having a king bigger. Okay, so by reasoning, you can see that this is totally independent. But again, you can also check if this is the same, right? Let's check. Let's do this verification. So the probability of drawing a king from a deck of cards, there are 4 kings amongst 52 cards, right? So this is an equiprobable sample space. I can use my counting problems in the numerator and denominator. Numerator are the situations that I am interested in the denominator are the situation, all the possible outcomes. And let's see this left-hand side here. What is the probability? So this is the, let me put it this way. This is the left-hand side I'm working out, and here is the right-hand side. So the right-hand side is this. Let's calculate the probability, the conditional probability, and we know the formula. Again, it's the intersection, or things happening at the same time, over what happens, over the divided by the probability of the thing that happened first. Okay? So let's work out this. You could actually calculate this through the formula, which is what I'm doing. So what's the probability of having a king and a club? Well, there's only one king of clubs, right? So this is the number of interest situation over all the cards, okay? This is the numerator. This is PK intersection C. Now, what's the probability of drawing a clubs? Well, we have 13 clubs over 52 cards. So in the end of the day, this probability here is 1 over 52. So you have the numerator and you multiply crossed by the denominator. This goes away and you're left with 1 over 13. So you can think about this. If if the left-hand side is equal to the right-hand side, then these are independent events. And it is the case because 4 over 52, if you simplify, is actually 1 over 13, right? Which is equal to 1 over 13 from the other side. So yes, P of K, in this case, P of K is equal to P of K given C. Okay? So these are independent events. Okay? So you drawing up a clubs don't tell you anything about augmented or increased chances of taking a king, of drawing a king. Okay? There, just as a side note here, you can calculate this conditional probability by not only using the formula, but also using the concept that you're inside an equiprobable sample space. So if you go back for 2 slides, you'll see that in equiprobable sample spaces, the formula for conditional probability gets simplified by the number of events, the number of outcomes of interest over the number of outcomes that happen first. So if we go back here, so this is the first way to calculate, this conditional probability using the definition. The second way, and this is good so that we can apply the counting problems, is to do P of K given C. Because we are in an equiprobable sample space, this is the number of things of interest. So it's having a king, so this is the number of outcomes that has kings and, or let me put an N here. These are the number of outcomes that has kings and clubs. So this is the number of outcomes where I draw a king and a club. So it's, well, there's only one king and a club, right? And here are the number of outcomes of clubs, right? What are the number of outcomes of what happened first? Meaning, what are the number of outcomes of clubs? Well, that's 13. So again, you have these 2 ways to calculate the conditional, and this is it's good so that we can train these 2 ways. You have the formula, and here you have like the concept, but in the end of the day, having drawn clubs first won't change the probability of drawing a king after that. Okay? Now I'll give you a counter example that isn't that the events are they're not independent. They're kind of depend on each other. So here is the other example. So let's take B as drawing a black card and C as drawing a club from this deck of cards. So what I want to check, if P of B is equal or not to the probability of P of B given C. And you could do the other way around. You could also analyze this problem with what's the probability of drawing a club? Is it equal if the club, if drawing a black card happened first? Okay. So you can test either way. It doesn't matter what event are you kind of taking as a prior to check, but the concepts are the same. So let's reason first. And I'm going to do just one of them. It doesn't matter which one you pick. The result will be the same. Let me stick to that first one there. Okay. So let's reason a little bit. You have a probability of taking a black card from the deck. And actually you have half red cards and half black cards, okay? Now, let's say that you draw club first. So you go there, you close your eyes, you draw a card, and then you look at it and it's a clubs. Well, then what's the probability of drawing a black card, right? Given that you draw a club, okay? And if you think about just in reasoning, if you draw a club, it's necessarily a black card, right? So before, drawing a black card was like 50%. But if you take a clubs first, then the probability of you having drawn a black card is actually 100%. So the probability of drawing a club is informing you, and it it changes your beliefs. It changes the likelihood of what's going to happen next. Okay, so let's calculate this using the same method we did before. What's the probability of drawing a black card? Well, it's the number of black cards, and we have 26, right? Black cards, which are from clubs and spades, over a total of 52. Okay, so this is the left-hand side. And now let's calculate this conditional probability. I have two ways of doing it. Let's do it again. Using the formula, it's PB given C, meaning that, again, the formula, both have to happen, but I have a correction term, which is the probability of what happens first. The probability of having a black card and clubs, right? So if you think about the equiprobable sample space, within the 52 cards, right? Within the 52 cards, and I'm working on the numerator here, within the 52 cards, what are the number of cards that are black and clubs, right? So, well, black and clubs are actually 1/4 of the deck, right? So it's actually 13 cards, okay? And now I have to normalize, which is what's the probability of draw a clubs? Well, it's 1/4, right? Because there are actually 13 cards of clubs within 52, okay? Or 1/4. So if you cross multiply this, right? 52 over 13, and you get rid of this part. 13 over 13, this is actually equal to 1. All right, so this is the first way to calculate. The second way to calculate is just using the equiprobable sample space property, which means that this ratio of probabilities just gets reduced to the number of outcomes. So this is the numerator is the number of outcomes of interests. This is B, sorry. So what are the number of cards that are black and clubs? Well, there are 13, okay? There are 13 black cards that are clubs. And what's the probability of having a clubs? What are the number of cards with the suit of clubs? Well, there are 13. So you will get to the answer anyways, reasoning from the formula or reasoning from the kind of equiprobable sample space simplification. But the thing is that when you compare both sides, this here is a half, right? This is, let me put it this way, this is a half. And actually this is different from the second hand side, which is equal to 1. So these events here, they are not independent. Meaning that if you draw a club, the probability of that card being black is 100%. While if you don't have this information, if you're not informed that you draw a club first, the probability of drawing a black card is only a half. Okay? So this is the concept of independent events. You can always check by doing this verification, but usually we can actually reason if things will change or not. Okay, but if you're in doubt, if you're questioning yourself, if you're sure of independence, then just do this check with the probabilities. Okay, meaning that the probability, the original probability kind of won't change if you're informed. If something happened first, then they're independent. If not, they're not independent. Okay, so now we're going to start a new topic, and this will actually ease our life a lot to calculate the probabilities and to use the properties of probabilities. So actually what we've been working on are properties of probabilities. So probabilities are bounded between 0 and 1. They are the probability of the sample space is 1. Complementary events, the probability of an event plus the probability of its complement needs to sum up to 1, and several other properties. So probabilities has lots of properties, and we were kind of studying these properties throughout formulas and definitions and everything. So now we're going to introduce probability trees, which are the counting trees, tweaked a little bit to solve problems of probabilities, which are much easier to do than the formulas, right? Okay, so here's how it works. To kind of complete or to sketch a probability tree, to draw a probability tree, you have 4 rules, right? They're here, they're listed here. Let's go through the rules one by one. So the probability tree is just like a counting tree. It branches into options, and the value placed on a branch is the conditional probability with the nodes further left as the given event. So let's break this property down. So the value placed on a branch, let's say this value of 0.8, okay, is the conditional probability of the nodes on the left, so y and a as the given event. So what happened first? So actually this probability here is the conditional probability of the event P happening, given that Y and A happened first. Okay? So whatever value you use in a branch, the value of a branch is a conditional probability. So let's say that this here is 0.1. Can you let's derive what is this 0.1 what is this 0.1 probability? So this 0.1 probability is actually the probability of x, because it's in the branch of x, right? Of the event x happening given that whatever on the left came first, given b. So this is 0.8, this here is 0.1, okay? And so on, right? So we could kind of populate all this tree, and just to do one more, let's say that this is let's say that this is well, this has to be equal to 1. But anyways, let's do this one. Let's say that this is 0.5, okay? So what's this probability? This probability is the probability of the event of that branch, so the probability of P, given that what events happened first? Well, the first event was Z and B, but they happened, right? Both of them happened. So this is B and Z happening at the same time, okay? So again, the tree is in structure that branches to the right, and it gives you a sequence of events that happen. So first happened A, and then Y, and sitting on this branch then is the probability of having P happening. So if you think about, like, if you're sitting here in this node, if you're looking, if you look back, right, you will see that, well, Y happened and A happened. And if you look ahead, you will have a probability of P happening. So it's a conditional, because you know already that A and Y happened first. And this conditional will be 0.8, okay? And the second property will come from this notion of kind of the sequence of events, because when you're sitting in an event and you look forward, the chances of P happening or key happening of Q happening has to sum up to 1, because either one of them will happen, right? So if you're sitting here, your first branch is 0.8, naturally your second branch will have to be 0.2. And this will makes us arrive at the second property. That is, the sum of the values on branches coming out of a node are 1. Okay, so let's take a look at this probability tree. We have first event E happening, right? And the probability, this probability here of 0.4, right, is actually the probability of event E happening given whatever came first. Well, but this is the starting point of the tree, so I don't have anything coming first. And this probability here, this is the probability of F happening, right? Because I'm in the branch of F, but given E happened already, okay? And this here is the probability of F not happening given E. Okay, so remember, whatever is on branches are conditional probabilities. Now here's the property. If you're sitting in a node, and well, this is the first event happening. So E happened and you're sitting on E, like in the instant of time that E happened. If you look at the possibilities of what's going to happen next, you have two possibilities. Whatever number they're branching, they have to sum up to 1, okay? So in this case, if this probability is a half, it necessarily means that the other probability is also a half, okay? Let's think about this. Let's sit on this node now, okay? Let's sit on this node now, and let's look ahead. Well, E did not happen. Okay, I'm telling you that E did not happen. When I look forward, I have two possibilities, F happening or F not happening, right? And again, that's the property of the complementary events, or the example that I always give in class of the pregnant, not pregnant. If you're looking forward and you have these two complementary events, if the chance of one is 0.2, the chance of other needs to be 0.8, because the value of things that are branching out of a node needs to sum up to 1. Okay? And what about this value here? Well, think about this. You can use the same property. If you're here in this starting point, your first event can be E. The first event E can happen or E cannot happen. And if one of the events is P of E, right, is 0.4, the probability of P of E complement, which is this branch here, right, because you're in the branch of E complement with nothing coming before, will have to sum up to 1. So it has to be 0.4 plus 0.6, giving you a 1% probability. Okay? All right, so these are the first two rules. The first rule is that in the branches we have conditionals, right? In this case here, when you're in the first event, the conditional kinds of turns out to be the prior, the first probability. And the second property is that every branch, whatever you branch, you have to sum up to 1, okay? When we were dealing with counting, the number of things coming into the node were the number of things coming out to the node. That is not true anymore. We kind of tweaked that counting tree to turn up so that we could turn the counting tree into a probability tree. And now we have to use this new property where actually all branchings need to sum up to 1. Okay? All right, so let's see the third rule. The third rule is this. The product of the probabilities along a particular path is equal to the probability that those events all happened. Okay? So think about this. Think about your initial state here. Let's say that you take this path, meaning that event A happened. It had 0.4, a 40% chance of happening, but it did happen. Then B happened, which had 70% of chance of happening given that A happened. And then C did not happen, which was 10% of chance given that B happened and A happened. In the end of the day, if you multiply all these values, so 0.4 times 0.7 times 0.1, this will be equal to the probability of all these events happening. So A happened, B happened, and C did not happen. So this, let me move just a little bit. So this will have, ouch. So this will have the final value of this will be the probability of A happening and B happening and C not happening, right? Because this is the sequence of steps, okay? So the multiplication of this tree will always give you the intersection, okay? So let's choose another intersection here. Let's say this intersection here. So what is the probability, if I ask you, what's the probability given by the multiplication of these probabilities here? So I'm taking a path, right? What probability am I talking about when I multiply 0.6 times 0.1 times 0.75? Well, I'm talking about this three events happening. Not A complement, or not A, and B and C. Okay? All right, so this is the third property, okay? And the final property is this. The probability of a particular event is the sum of probabilities of those paths representing the event. So let's break this rule down. What we have is this. The probability of a particular event, let's say I'm talking about X. Let's say that I'm talking about X. So the probability of X happen, right, is the sum of the probabilities of the paths that represent X. So let's highlight the path that represents X. Well, we can have X by having E first. We can also have X by having F first. And we can also have X by having G first. Okay, so I'm highlighting the paths that represent the existence of X, or the happening of X. Okay? It represents that X has happened. So in the end of the day, if I want to calculate the probability of X, I cannot just account for one path, right? I have to account for all the three, of all the probability of all the three paths. So what's the first path? Let me get this some space here. So the probability of the first path is the probability of X happening and E happening, and just E. E was the first event. Okay. So the probability of this path is given by 0.5 times 0.8. Okay. Again, don't be confused. This is the intersection. This is the resulting probability of the path. It's different from this number here. This number here is telling me that E has happened. And here I'm looking forward. If you're sitting here, I'm looking forward to X happening. Okay, they are different. They are not the same. Okay? So, and you can see that they're not the same if you think about the definition of conditional probability. Okay, the definition of conditional probability is this conditional probability here is equal to the intersection, but normalized by a factor. So they cannot be the same. Okay. And you can think about the clubs and black cards example, right? So if you think about this, for example, but I'm using E and X. You could let's modify this. I'm not going to modify the tree because the probabilities would change. But think about the probability that you draw that you've drawn a black card. You want to know what's the probability of that black card being a clubs, right? Or that, let's say that you draw a clubs, and what's the probability of that being a black card? Well, that's 100%, right? But the probability of having a black card and a clubs is half, right? Because you could have spades as well. So they are different definitions, and I would suggest you to pause the video and think about the black cards and about this probabilities here, the differences, and you can go back to the problems we've solved. What's the difference of this probabilities here? Okay. Well, what's the other? Let's continue. What's the other path that represents X happening? Well, it's x and f happening. This is 0.5 times 0.2. So this is the probability of having x from the path of f happening first and then x. And finally, the probability of g and x, meaning that first x happens, then x happens, okay? G happens and then x happens. What this rule is telling us is that the sum of these paths represent the event. So P of x is actually the sum of all these paths, okay? X inter E plus P of x inter F plus P of G inter X. So this is what we call, what we used to, we commonly say that the probability of an event is actually the sum of all the possible ways you can have that event, okay? And that's it. So I know that lots of information, but once you master these properties of the tree, lots of exercises will be very, very much faster and easier to solve, okay? So let's stop to do an exercise. Let's stop to do this tree. I've sketched a tree, and the tree is like this. I can have an event E happening first or not, right? And after that E happened, 3 other events can happen, okay? All right, so this is a probability tree, and I ask questions, right? So first of all, when you see a probability tree, you should always think on completing it first, okay? And let's use the rules that we have, okay? So the first, like one of the easiest rules is that whatever is branching has to sum up to 1, right? So from this node here, we're branching in 3 possibilities. The possibility of f is 0.4, the possibility of h is 0.4. So the possibility of 2, the likelihood that the probability needs to be 0.2, because 0.4 plus 0.4 equals to 0.8. But when you're sitting here and you're looking forward, FG, the output needs to be F, G, or H. So if the other 2 takes 80% of the chance of happening, G is left with 20%. Okay, so the sum of these branches needs to sum up to 1. Okay, so this is one first completion that we can do. The other completion is here. So 0.5, 0.2, and we're branching. This sums up to 0.7, but we know that all of the branches needs to sum up to 1. So we have 0.7. To get to 1, we need 0.3. Okay, so this branch is 0.3. All right, so after completing the tree, now we can work on the questions. So let's see, P of E, but the probability, so I'm asking a probability of event E not happening, or E complement intersection F. Remember, the intersection F, so E complement, intersection F is this path here that I'm talking about. So E complement and then F. Would this answer be 0.5? Would this answer be 0.5? What do you think? No, whatever is in the branch is a conditional probability. The intersection is the multiplication of the path. Remember, it's the third rule. The intersection is the multiplication of the path. So in this case, it's 0.4 times 0.5, and it's not 0.5, okay? All right. The other question is this. What is the probability of having what is the probability of having E union G? Okay, so let me get another color here. Let me get this. So the probability of E happening, right? So this path here is the probability of E happening, right? Or G, right? Or G. So I'm gonna highlight G being, so what's the probability of G happening? Well, it's the sum of all the possibilities that represent G. So this is G, okay? So, and we know the formula, we know the property of the probability of a union. The probability of a union is the individual probabilities of the events minus the probability of the intersection. We learned this property, okay? We've learned this. And so let's work this out. Let me get rid of that. Let me go. So we know that the probability of E is 0.6, right? This is this branch. It is a conditional probability, but it's the first, so it's kind of the prior, plus the probability of G, which we know, right? It's the sum of the both yellow things. So both of the yellow paths. So it's the probability of G intersection E for this first path, plus the probability of G intersection E complement. Okay, so this here is the probability of G, which is this first term. So I'm going to copy 0.6 plus this first term here is the multiplication, the intersection. Remember, the intersection is the multiplication. It's E happen and G happen. It's when you sit after everything, when you're here, like E and G happened. So you have to multiply everything. So it would be 0.6 times 0.2 plus the other path, which is 0.4 times 0.2. 0.4 times 0.2. Then we have the intersection, E intersection G. And this symbol here is a subtraction. Okay, so who is the subtraction? Which number is the subtraction? Well, I have to subtract E and G. So I have to subtract this, like this branch again. Okay, I have to subtract this branch again. You can think about this. I didn't even need to kind of calculate because this was going to kind of get rid of with that. So I have to kind of take off this quantity, which is equal to this, right? So this is kind of killing it. And this is 0.6 plus 0.4 times 0.2. Okay. In the end of the day, this is equal to, so 0.4, this is times 0.2, this is 0.08 plus 0.6, this is the final answer, okay? Now, I could have done this visually. I could have done this totally visually without working out the formula for the union. And how could I do that? Well, you think about this. The probability of one or another, you just include, if the branch is repeating, do you agree that this first yellow branch is kind of repeating with the purple branch, E and then G, right? So you can have E and then G embedded in the first, in this purple condition. They are repeating itself. So just what you can do is have the path, but just once. So you would have the probability of the probability of E plus, then you would have only the probability of this guy here, okay, summed up. And that's the result, okay? The last question is this. The last question is this. What's the probability of the event H happening given that E happened first? So if event H happened, so I'm talking about kind of this branch here. So it's sitting on the branch, right? So it's 0.4. Right, so this is 0.4. Okay. All right. So this is what we have to kind of learn with probability trees. And let's do another exercise. I have a small deck of cards. Okay, I have 8 clubs and 4 hearts, so I have just 12 cards. They are fair. I have an equiprobable space, although I have a different number of cards. They are all, there's no heavier card or anything like that. And what I'm telling you is that I will have 2 draws. What's the probability of having both the same suit? So I want the probability of having, for example, hearts and a heart and a heart. The probability of having a clubs and a clubs, a probability of having a spades and a spades, and the probability of having a diamond, and a diamond. Okay, so I'm interested in this outcome. So the probability of having the same suit. So the same suit is equal to the probability of this happening, or this happening, or this happening, or this happening. Okay? Now, you could work the formulas out, no doubt, but now you know trees. So let's try to get this. Trees are the sequence of events. So the first to draw, oh, and actually I just have clubs and hearts. It's my small card. So this would be in a normal deck, right? Here I have just clubs and hearts. So this is not applied. Okay. So in the first draw, I can have a hearts or clubs, right? And in the second draw, I can have a heart and a clubs, a heart and a clubs. Okay. Now let's populate the tree. Remember, this is not a counting tree. This is a probability tree. So what's the probability tree that we're talking about? So here's the tree. This is hearts. You can, for the first row, you can have hearts and clubs. As a second option, hearts and clubs and hearts and clubs. Okay, so let's populate this tree. Remember, this is not a counting tree. This is a probability tree, meaning that what sits on the branches are conditionals, and the branches has to sum up to 1. Okay, so first of all, we are in a equiprobable sample space. What's the probability that in the first to draw I have hearts? Well, I have the number of interest outcomes, which are 4 hearts, over the total outcomes, which is 12 cards. So this is the first probability. Now, I can go here and do the same reasoning for clubs, meaning that I have 8 clubs over 12 probabilities, right? For my first draw, but I don't need 2. I just have to say, well, if this is branching and it has to sum up to 1, 4 over 12 to be 1, we have 8 over 12. Okay? because 4 over 12 plus 8 over 12 is equal to 12 over 12, which is 1. So how much 1/12s I have to sum up to 4/12s to have a whole, or 12/12s, okay? So you can either use like the definition of probability in equiprobable sample spaces, or you just sum up these branches, okay? Now let's talk about the second draw. Well, the second draw, again, you will have to calculate the probability. Well, what's the probability of the second draw if I have hearts? So pay attention of what I said. I said that I already took a heart. This probability here will change because this is actually a conditional probability. So given that I took a heart, how many hearts I'm left with? Well, 3. So the numerator is the number of events in my interest, and I'm left with only 3 hearts, okay? Over the amount of total cards. For the second draw, the amount of total cards is actually 11, okay? I can think the same way to this branch, but I'm just going to use the property where how much do I have to sum up to 3 to get to 11 11ths, or a whole, right? So I have to sum up 8 11ths plus 3 11ths to have 11 11ths. And look at this branch here. This is a conditional probability. This is the conditional probability of having a hearts, given that I had a clubs first. So how many hearts I will have if I have a clubs? If I had a clubs first? Well, the hearts didn't change. You will have 4. And the number of total cards will be 11. And I'll use the same property that I need to sum up 7 11ths to 4 11ths to have a complete 11 11ths, or a whole, okay? Now look at this. This you can see that the conditional probabilities are different, right? So this is the probability of hearts given that I had hearts, and this is the probability of hearts given that I have clubs. And they are different. So meaning that the event that happens first changes the likelihood of what's going to happen next. Okay? Now what's the question? The question is, what is the probability of having both of the same suit? Well, the probability of having both of the same suit is having this situation, probability of hearts and hearts. So it's having both events happening, or the probability of having C plus C and C, clubs and clubs. So let's do that. The probability of having the same suit is equal to the probability of hearts and hearts, which is the multiplication of 4 over 12 times 3 over 11. Plus, and you see that you don't have to kind of discount any branches, they're not overlapping. So as the other example we did, so this is the probability of the clubs and clubs happening, which is 8 12ths times 7 11ths. Okay? And that's it. This is the probability of having the same suit. Okay? So having trees is very interesting to solve a little bit more elaborate and intricate problems. I invite you to stop the video and try to solve the problem on the seeing deer and squirrels. I think it's it's this one. No, sorry. So I think it's this. I'm not sure. Go back. Find the examples of squirrels and yeah, I don't know where the example is, and the deers, and start designing your tree like, oh, I can see a deer or not see a deer, and then I can see a squirrel or not see a squirrel, right? And you will see, and then start populating the probabilities. you'll see that this will turn out to be very fast because you now have like the properties of the tree. And if I'm not wrong, they asked like, what's the probability of seeing a deer and not a squirrel or something like that. So you know that will be just the multiplication of the path, right? It's the multiplication of the probabilities sitting on the path. So all that formulas and time we consumed to solve the squirrel problem, I invite you to try and solve with the probability tree, and you will see that it will be way, way, way easier. Okay? All right, thank you so much.